Signal encoding techniques. In data communication, data or information um, transmission can either take two main forms. You probably learned about this in your data communication and networking one course, the part one section of it, or the part one of it. Or if not, from your microcomputer uh, systems and application course, you might have learned about that data or information is transmitted in two forms, which is either analog or digital. And this topic here is really all about how these um, transmission signals are managed, in terms of its representation within a given system or application. Transmission signals can be based on different frequency spectrum bands as well, which is usually termed the carrier frequency. So with data taken either analog or digital form, it also in its signal form, transmission can either be based on different frequency spectrums. Now, both analog and digital data is encoded or can be encoded, which is what this topic's about, as either analog or digital signal. Okay. So whether you have an information in its digital state or in its analog state, if you really want to have it represented properly within a given system, then we need to find a way to do that, and that's where the encoding comes in. So both analog or digital data can be encoded as either a digital or analog signal. Analog signals, okay, before that, let me go over this, the overviews. So some of the objectives of this topic, we'll be covering digital data conversion to to digital signal. So how do you represent a digital data and information into digital state or digital state to the signal form? You have to keep in mind that electronic devices or systems generally transmit signals. It's every information that we access or send within an electronic medium. It's usually via signals. Okay. So now the question is, if the information we had is already digitized, how do we generate a signal for it so a system can actually pick it up and transmit it? And usually when you do have a digital data conversion to digital signal, we term that digitizing the information. Okay, so that's why we digitize information so you can have that appropriate state for a computer system to consider digital and able to transmit it within a given medium. Some terminologies that we'll look at. Of course, it's very important to know some of the terminologies that are involved in signal transmission, so at least when you are describing them, you know how to related to the ordinance. We'll also be looking at the interpretation of the signals. How do you interpret it? If you use a particular means of representing information, how do you interpret it? We're also going to be looking at some of the encoding and modulation schemes, the various techniques that are used to format groups, so to format and group some of the techniques that we have. We'll look at some of the advantages and disadvantages. And then we'll also look at how to move information or data from a digitized state, a digitized form to an analog form. And now this is where you look at the modulation, and it's more or less a respective form or in its appropriate form, because you have to think about the two different forms that information or that data can take. You have analog and digital. Now, the very moment you move between them, there has to be a different approach in terms of its interpretation. Okay, so usually when you're trying to convert a digital data in its a digital form to an analog form with a signal or data, then you would have to look at a different way of interpreting, in this case, modulation. So you modulate digital to analog or analog to digital, and you digitize this digital signal to analog data, sorry, to digital data, or digital data to digital signal. So when we talk about digital, it's purely digitization, and that's where encoders and decoders comes into play. But whenever you talk about moving from two separate forms of data transmission, then you're looking at modulations. Okay, so in general terms, encoding, when you're purely dealing with digital information or digital signaling, and then modulation when you're looking at purely analogs, or when you're moving from one transmission form to another. Okay. So to represent that within this diagram, you have, if you want to digitize specific information, encoding techniques are employed, especially when information needs to change its form from a given digital state to a digital signal. If I'm not confusing anybody, so let's look at it from this diagram in perspective here. So you'd have digital or analog data that needs to be digitized. So it needs to just take a digital form. And information or data coming through, we need to make sure it's at the end of at the receiving end or in the transmission level, or within transmission level, it's purely digitized, purely in a digital signal form. And that's where you introduce encoders or encoding schemes. And here we have encoders and decoders play a key role in how the information are digitized. Okay. So as I mentioned earlier on, pure digital, you use encodings techniques. All right. Now, when it comes to analog, say you want to, whether the information is in digital state or analog state, and you want to have it within an analog signal form, then you modulate it. So this way, modulators and demodulators comes into play to give us that analog signal we're looking for. But when it's purely digital, then we use encodings to address that. So keep that in mind, information in its either it's in a digital or analog state. To give you purely digital information at the receiving end at the receiving end in the form of a signal, which is digitized, then you have to digitize it. That's where you return the word digitize using encoders and decoders. So you have these shapes come out representing the digitized signal of the particular data or analog data that was fed in to the system. And that the same applies to the analog as well. It could either be a digital data or analog data coming through, but for as long as they're at the other end of it, the carrier wants it to be purely analog. A good example would be telephone calls or telephone transmission. Okay. Then at the other end, you have to probably use modulators and demodulators to give that consistent signal transmission that you need. So here you notice that the carrier comes into, because I indicated earlier on that transmission signal can be based on different frequency spectrum bands that are considered the carrier frequencies. Okay, now let's delve a little bit more into it so we can look at the variations within the signal, either from analog or digital data to either analog or digital signal form. Okay, there of course is going to be a number of conversions going on over here. We can either have digital data going to analog signal or digital data going to digital signal. And then the other way around as well, either analog data going to digital signal or analog or digital data going to analog signal. Okay, so now let's look at some of these things real quick. Now, digital signal or a discontinuous discrete voltage pulse. So in other words, signal that have got digital representations are not continuous with respect to the electrical signal, the voltage pulse that goes with it. And each pulse of the signal is termed the signal element. They either have one of two states. It can either be a high state or a low state, which is represented in binary digit formats. So generally, when we're trying to represent digital signals, we use the binary representation. It's a lot more discrete and easier to relate to in terms of, or easier to manipulate in its digital form representation. The analog, on the other hand, though, that have continuous electrical signal pulse with time as a varying feature. Now, the particular encoding technique that would be used to either digitize or modulate a particular signal or a given signal, it depends on specific requirements, which could either be based on the media that's being used for the transmission, the media which the devices being used, and as well as the communication facilities that's available, which could either be the mediums either via twisted pair cable or coaxial cable or fiber optic cable, or by the unguided approach, which is the wireless approach or the radio wave approach. So some of the key dependencies or requirements needed if you want to use a given encoding scheme. You have to look at some of these specific requirements. Okay. Terminologies that usually comes up when it comes to signal encodings. We do have unipolar signaling. In general, when we talk about a signal being unipolar, it just simply means that the signal element has the same voltage pulse signs, that is either positive or negative. Now, that's one thing that comes to mind usually. I get that question a lot, even when I started understanding some of these terminologies or signal encoding in general. When we talk about the signal having a positive voltage or a negative voltage, what does that really mean? I mean, does that mean that the this in its simplest form, does that mean the signal can be a plus or a minus? And what really makes that? And let me clarify this. Usually when we talk about a signal being positive or negative, it's just a term that is used in signal plotting to address the various voltages uh, that is that is that is affecting a given signal being generated. Okay, so like for instance, if a signal was supposed to have maybe a 5 volts power attached or electrical voltage pulse attached to it, and you don't get that given specific 5 volts uh, voltage current running through with that, what happens? How do you, is this still going to be a positive? Would it be represented as a positive or a negative? Since you do electrical signals, you're going to really, and it's voltage in enhanced. It's enhanced using voltages. The question: what if you don't have enough voltage coming through? Would would the signal be the same value or same representation or not? So generally, the fluctuation of the signals within that particular transmission or within that particular system is what plotters or signal developers have come to uh, formulate using the positive or negative representations. Uh, Knowing very well that signals generally can have fluctuations here and there depending on the voltage current being passed through it or being used to amplify or to push the signal. Okay, so if the signal was to drop to a given level, how do you interpret that? Or when it goes over a given level, how do you interpret it? Let's say if it goes beyond the 5 volts, or it goes below the 5 volts, or even goes to a state where it's even it can even be represented within either within a 5 volt representation or something else. Then the question is, how do you uh, value it? So how do you uh, assign to it? And that's where the positive and negative comes into play. So don't get confused about that. It's just a terminology is used to address the signal fluctuation at the voltage levels. Okay, so unipolar just uh, It's represented by a signal element with the same voltage pole signs. So if it's either a negative or a positive, as I illustrated, as I basically pointed out, the voltage, the positive and negativeness is all relate. It's all in relation to the voltage fluctuations of that particular transmission or that particular signal. Okay, we'll look at some of these within the encoding technique, so you can get it how engineers have figured some of these things to help us basically make sense of data being transmitted. Okay, since we're dealing with electrical signals within an electronic device. Polar signal on the other hand, signal element encompasses two uh, various voltage levels. Um, if you look at the unipolar, unlike the unipolar, for instance, where you have is just the same voltage pulse, it could either be positive or negative. The polar, on the other hand, has one logic state represented by positive and the other represented by negative. Are we good? So in other words, we have two logic states or logic levels within a polar signaling. Okay. We'll look at this also within the encoding techniques at the multi-level binary techniques, where you notice signals have either a minus or a plus voltage levels. Okay, or a negative or a positive voltage levels. So to put it into another perspective, when you want to look at unipolar and polar, unit is just same. The signal just has the same voltage pulse sign or level. It's either positive or negative. And polar is either a positive or a negative. So you'd have these two states or two voltage levels being uh, part of the signal, or it's within a signal. So whenever you have a signal that has got that uh, uh, representation within the signal levels, then you know it's a polar. Okay. The other terminologies that you'd have that we looked at that we want to look at is data rates. Data rates usually transmissions within bits per second. So you assuming that you have a data that's been transmitted, the time the entire data takes to complete a single transmission is what we term the data rate, and it's usually measured in bits per second. Okay, and duration, duration of a bit or the length of a bit is the time it takes to transmit or to emit a single bit, which is usually 1 divided by the data rate. Okay, so whereas the data rate is the full transmission particular message, the duration or length of a bit, it's usually the time a single bit takes a transition from one bit to another. And that's very important in determining the speed of a given transmission or a given message that's been digitized. And then you also have modulation rates. So when it comes to calculation, keep that in mind. the various signs or the various variables that you're going to be looking at for data rate is R for the rate of the data, and then the durations of a given bit is usually 1 divided by R, which is your data rate. Okay, so keep that in mind so that when you have assignments that has got some of these calculations and you know how to look at them. If I were to give you the data rate and I ask you to calculate the duration of a single bit, you know it's going to be 1 divided by the data rate. If I were to give you the duration instead for a given bit and I ask you to calculate the data rate, then you know how to go about that as well. Given a sequence of bits, then you can say, okay, to calculate that, I'm going to have to multiply the entire number of bits. If it's an 8-bit sequence, it's going to be 8 times the duration of a specific bit to give you the data rate. There are a whole bunch of formulas within that we'll look at later on in terms of calculations. Okay, modulation rate is the time taken. This is probably at the analog level. Modulation rates. So modulation rate, yes. It's time. The rate at which a signal level changes. If we're looking at analog signals, the way they form, the way they are plotted, you will notice they come in a wiggly or sine wave format, and the change within the pitch of the signals is usually what is termed the modulation rate. So the rate at which the signal level changes from maybe a higher pitch to a lower pitch is what you term the modulation rate, and usually measured in buds. So we have a particular signal having a bud rate of maybe 9,600. Tells you that a signal fluctuates from high to low at that given signal level, and usually measured as a signal element in seconds. And you have a marking space which uses the binary zeros and ones that we have. Other terminologies: it's elements, bits, single binary or zero, it's single binary 1 or 0, data rate, signal elements, and we've taken some of these already. Interpreting signals, what are some of the things that you need to know? Well, first of all, you need to know about the timing of a given bit. So if you want to interpret signal, you need to know the time of bits. That's when the bit starts and when it ends. And when it comes at the analog level, you want to look at the levels of the given signal. Factors that might affect a signal interpretation. Probably you're going to be looking at the signal to noise ratio, the interferences, the attenuations that goes with the signals, and the interruptions. So the noise ratio is a key part. What about bandwidth? If you have a small bandwidth or a big bandwidth, how does that affect the interpretation of the signal? Okay, and then the type of encoding scheme used. If you were to use a wrong encoding scheme for a given transmission, you could end up with wrong information or wrong data being transmitted from the transmitting end to the receiving end. Okay, so now let us delve into the encoding schemes that we have. They're usually grouped for a specific reason, I would guess. We have the no